And now we're going to move into those aforementioned imaginary numbers. So we're looking at 2.7, which is complex numbers. And our first problem, we're going to simplify a number using I, and I just stands for imaginary. So the question is, how do you write the square root of negative 18 by using the imaginary unit I? Now this is going to require you to dip back into your Algebra 1 and remember how to simplify a radicand. So what we're looking at is we need to find a factor pair for 18 that includes a perfect square. So when we do our factor pairs, we get 1 and 18, 2 and 9, and 6 and 3. And what we want to do is we want to go from the largest number in the factor pairs down to the smallest number. So you can see we've got arrows there pointing from 18 down to 6 and then 3 up to 1. We always want to take the largest perfect square factor that we can find, because then we don't have to do any more factoring after that. We are going to be assured that our answer is going to be in simplest terms. So the largest perfect square factor of 18 is 9. So we pair that with the 2. So you can see we've got the square root of negative 9 times 2. Now what's going to happen with that negative? You cannot take the square root of a negative number. It's not a real number. So what we do is we take that negative out and we replace it on the outside with an I, which lets us know that this is an imaginary number. So then remember that you can separate the radicand, or you can separate what's inside the radicand if you've got multiplication or division. And so that leaves us with I times the square root of 9 times the square root of 2. Well, what's the square root of 9? It's 3. So then we place the 3 in front of the I, and we get 3I square root of 2. The radicand can't be broken down any further, so that is our solution. Okay, now we're going to take a look at complex number operations. These are very similar to the operations that you use with any other sort of variable. So if you had 3x plus 2x, you would know that your solution was 5x because you just add the coefficients. You know that the x's are the same and the exponents on the x's are the same, so then the coefficients can be added. Well, the same rules apply here. If you have 3i plus 2i, your i's are exactly the same. They're both the same variable, and they have the exact same exponents. So since they're the same variable and have the same exponents, we can then just add the coefficients, and we get 5i, and that's the solution. In problem number 3a, we're going to treat our complex number expression in the exact same way that we would treat any other variable expression. So we look at 4 minus 3i plus negative 4 plus 3i. And both of the complex number expressions are located within parentheses. So what we're going to do is we're going to see if there's anything we can do inside the parentheses to simplify them. And there's nothing we can do. Then, since we've got a positive sign in between them, we know that we would distribute a positive 1 through to the negative 4 plus 3i, but that doesn't change anything. So we can just go ahead and drop the parentheses. That leaves us with 4 minus 3i minus 4 plus 3i. At this point, we just consolidate like terms, or we combine like terms. So 4 minus 4 is 0, and negative 3i plus 3i is also 0, so the solution to this expression is 0. So in 3b, we're going to do the same method, except this time we have a negative in between the two quantities. So we've got 5 minus 3i minus the quantity negative 2 plus 4i. So we look at the inside of 5 minus 3i. There's nothing there that we can simplify, so we just pull that down and drop the parentheses. But since we've got this negative sitting out in front of the second quantity, we've got to distribute a negative 1 through to both terms. So we get negative times negative 2 is positive 2, and negative times 4i is negative 4i. So now we combine like terms. 5 plus 2 is 7, and negative 3i minus 4i is negative 7i. So your solution is 7 minus 7i. Now we've already discussed a little bit about imaginary numbers, but let's take a look at what imaginary numbers do with different exponents. So anytime that we have I with an exponent of 1, which we assume to be 1, it's going to be equal to the square root of negative 1. Anytime that we have I squared, it's going to be equal to negative 1. then anytime that we have I cubed, that is negative I, because I cubed is simply I squared times I. So we get the square root of negative 1, which is I, times negative 1, because that's our replacement for I squared, and so we get negative I. Then for I to the fourth is the same thing as I squared times I squared, and since we have I squared, that's equal to negative 1, so negative 1 times negative 1 is 1. Now if we were to take this out to I to the fifth, we would just repeat the pattern, and I to the fifth would be the square root of negative 1, I to the sixth would be negative 1, I to the seventh would be negative I, and I to the eighth would be 1. So all you're going to do with this is anytime that you have, or if you were to divide the exponent by 4, anytime that you have a remainder of 1, it's going to be I. Anytime you have a remainder of 2, it's going to be I squared. Anytime you have a remainder of 3, it's going to be I cubed. And anytime you have a remainder of 0, this is important, anytime you have a remainder of 0, it's going to be I to the fourth. So again, if we divide the exponent on the I by 4, the remainder tells us which one of those i's it's going to be, and then which number that is equal to. We'll take a look at a problem where we use what we just learned here. So we're asked, what is each product? And we're given 3i times negative 5 plus 2i. So we're going to distribute that 3i to both terms, the negative 5 and the 2i. 3i times negative 5 is negative 15i, and 3i times 2i is 6i squared. So we end up with negative 15i plus 6i squared. Now what we're going to do is we're going to take that I squared, and what is I squared equivalent to? It's equivalent to negative 1. So we change it to negative 1, and we solve the problem from there. So the negative 15i is not going to change. We're not going to change that to a negative square root of 1. We want to leave it as I because that's the simplest form. But then we do 6 times negative 1. So we get negative 6 minus 15i. And this is going to be your standard form for writing a complex number. You're always going to put the constant ahead of the imaginary number. So it's going to be different. It's going to be opposite of what you would normally do with a variable. So in 4b, we're going to do the same thing, except this time we have binomials. So we'll go ahead and use FOIL. So we get 4 times negative 1 gives us negative 4. 4 times negative 2i gives us negative 8i. 3i times negative 1 gives us negative 3i. And 3i times negative 2i gives us negative 6i squared. So replace that I squared with a negative 1, and then we'll see that we get negative 4 minus 8i minus 3i plus 6. Combine any like terms, so negative 4 plus 6 is 2, and negative 8i minus 3i is negative 11i, so you're left with 2 minus 11i as your solution. So in problem number 5a, we're going to start taking a look at dividing complex numbers. So we're asked, what is each quotient? We're given 9 plus 12i over 3i. Very important rule to remember is that you are not allowed to have an imaginary number in the denominator of a fraction. So that means you have to do what is called rationalizing the denominator, which we're going to do by multiplying by the conjugate of the denominator. So the conjugate of 3i is negative 3i. But remember that in order to maintain the integrity of the fraction, whatever you do to the denominator, you also have to do to the numerator. So if we multiply the denominator by negative 3i, we also have to multiply the numerator by negative 3i. So when we do this, we're going to have to distribute through the negative 3i to the 9 plus 12i. That gives us negative 27i minus 36i squared in the numerator. Then in the denominator, you get negative 9i squared. Now this is the point where we can start getting rid of that imaginary number. Because we now have an I squared, we can substitute in a negative 1. And we have I squareds in both the numerator and denominator, so that's what we're going to do. So now you're going to have negative 27i minus 36 times negative 1 over negative 9 times negative 1. That leads to 36 minus 27i over 9. Now, remember that you can take a single fraction that has multiple terms in the numerator and you can actually split it into different fractions. You could do that here if you wanted to. I'm just going to leave it all as one fraction and just understand that I can do the same operations on this one fraction that I could do on multiple fractions. What that means, I can divide the 36 by the 9, and I can divide the negative 27 by the 9. So divide 36 by 9, that leaves you with 4. Divide negative 27 by 9, that leaves you with negative 3i, and there's your solution. Your solution is going to be 4 minus 3i. In 5b, we're still going to find the quotient, but this time we have a binomial in the denominator. So again, you have to multiply by the conjugate, and the conjugate of 1 minus 4i is 1 plus 4i. So we're going to multiply both the numerator and the denominator by that. And since we've got binomials that we're multiplying against each other, we're going to use our FOIL method. So when we FOIL the numerator, we're left with 2 plus 8i plus 3i plus 12i squared. That's going to be over top of 1 minus 16i squared. Now remember that because these are conjugates, they follow the same rule as you would have with difference of squares. And whenever you're FOILing out like a difference of squares, you never have to do the O and the I. You only have to multiply out the F and the L. That's why we only have 2 terms in the numerator. Now take your I squareds and simplify them down to negative 1. So 2 plus 8i plus 3i plus 12 times negative 1 over 1 minus 16 times negative 1. So negative 16 times negative 1 is 16, and 12 times negative 1 is negative 12. So we're left with 2 plus 8i plus 3i minus 12 over 1 plus 16. Combine your like terms, negative 10 plus 11i over 17. Okay, we're now going to look into factoring imaginary numbers. And the format that we have for imaginary numbers is x squared plus y squared. So this should look familiar, but just slightly different from difference of squares. This is actually like the sum of squares. If we were to take that y squared and move it over to the right side and just solve for x, we would end up with a square root of a negative number. So that's how you know that you've got imaginary numbers here. Now the format that you're going to have for imaginary numbers in their factor form is going to be x plus yi times x minus yi. So again, it's got to be 2 terms, it's got to be an addition problem, and you're going to have opposite signs in your factors. So now we're going to take that and we're going to test it. So we're asked, what is the factored form of 2x squared plus 32? So we're going to factor out that 2, and that's going to give us a sum of squares, x squared plus 16. So now we're looking at what is the square root of x squared. The square root of x squared is x. What is the square root of 16? It's 4. So we bring down our 2, and we set up our factor pairs. We're going to have a factor with a positive and a factor with a negative, and we're just going to take the x and bring it down into both positions, and then we're going to tack on an I to our 4 because we know that we've got an imaginary number. So our factors would be 2 times x plus 4i times x minus 4i. Now why does this work? If we solve for x, we'll see that we get the exact same thing. So 2x squared plus 32 equals 0. Move that 32 over to the right side. Now divide by 2 and you get x squared equals negative 16. In order to get rid of that square, we've got to take the square root, which gives us the square root of negative 16. And the square root of negative 16 is plus or minus 4i. And we know that if we have the factor pairs x plus 4i times x minus 4i, that our solutions will be plus or minus 4i. The final problem that we're going to work with imaginary numbers or complex numbers is to find the solutions of the equation 2x squared minus 3x plus 5. Now you could run this through GCF, perfect square trinomials, difference of squares, anything that we've already done, and you're not going to be able to find a factor pair solution for this. So you could either use the quadratic formula or you could use completing the square. I'm going to choose to use the quadratic formula to find the solution on this. So the original formula, or the original equation again, is 2x squared minus 3x plus 5. I'm going to pull down my quadratic formula and substitute the values for a, b, and c, and then I'm going to solve. So negative times negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times 5 over 2 times 2. Simplify this all out. 3 plus or minus the square root of 9 minus 40 over 4. 9 minus 40, the discriminant, is going to give us negative 31. And you can see that since the discriminant is negative, there are going to be no real number solutions. We're only going to have imaginaries. So we're going to pull out that negative and turn that into an I, and that's going to give us 3 plus or minus I square root of 31 over 4. Square root of 31 cannot be simplified any. 3 and 4 cannot be simplified, and I over 4 cannot be simplified. So that is going to be your solution.